Hi everyone, my name's Ellen and I along with Dev are the co-leads for motor control this term.
Today we'll be talking about the motor controller that we designed for Goose 5.5, which will be the pod we will be competing with for CHC.
Shown on the slide is a block diagram of our system. We'll give you guys a high-level overview of the system and then elaborate more on specific aspects of the design throughout the presentation.
This design began its cycle in May of 2021. Currently, we're using a 14S1P battery pack, which has a nominal value of 44.8 volts and a max of 51.8 volts. This is connected to the three-phase inverter. The MCU sends low voltage PWM signals, which are amplified by the gate driver, to drive the high power MOSFETs. We also have included various sensing for voltage, current, acceleration, and temperature. The CAN transceiver is integrated into the board so that we can connect the motor controller to the CAN bus, which Quinn talked about earlier today.
As you can see in the block diagram, we highlighted the high voltage and low voltage components of the motor controller. This is because we split the motor controller into two boards, a high voltage board, which I worked on, and a low voltage board, which Deb worked on.
We have used Altium Designer to create the schematics and layout for these boards and went through various technical roasts to create the first revisions of the boards shown on the screen. The boards will be communicating together via the 18x2 header seen on the screen.
We decided to split the boards into two to simplify the testing and prototyping of the motor controller. A major benefit to this is decreasing the troubleshooting and debugging process because issues within one board won't delay the testing of the other. In addition, this approach ensures that the motor controller remains modular, easy to assemble, and flexible for future revisions.
And as mentioned before, the logic board contains all the low voltage components of the motor controller. This includes the STM32 MCU. Currently, there are 3 versions of this board planned as of now. Once complete, not much should be changed as further renditions of the power board occur. And because of this, the reasoning behind the pinout selection is very crucial to make layout simpler in both the logic and power board. The logic board is primarily responsible for generating the SV PWM signals to send to the power board, which will in turn drive a 3-phase motor. Additionally, sensing data is taken constantly to make decisions when on autopilot mode. This also results in an added protection against overloads and electrical faults. And if you're not sure about what SV PWM signals are or what FOC control is, don't worry because we'll be going over these terms in more detail soon.
The power board, which houses the high voltage components, quotation marks around the high is because the board would be at most handling 51.8 volts as determined by the battery pack, which is not actually considered high, but as our goals move from thrust to propulsion, we'll be creating revisions that are able to support a much larger voltage input. Anyways, onto the actual system. There's a 5-volt input that will be retrieved from an LDO, which will be sent to the logic board. The gate driver requires a 3.3 volt input to power the gate driver, and the gate driver ensures that the signals are amplified enough so that it's able to drive the MOSFETs. In addition, the power board includes a voltage divider and shunt resistors for voltage and current sensing. I'll be elaborating more on this in later slides.
Now we're going to be talking about some control theory terms and concepts that are crucial for the motor controller. These include, but are not limited to, V over F scalar control, FOC or vector control, SV PWM, and a PID controller. There are 2 V over F control loops that I'll be talking about today, an open loop and closed loop configuration. In an open loop, this is just about the simplest V over F control loop, and what we do is we take the current time into perspective and use that to generate a desired speed. This is done to ensure that the speed increases linearly with time. The motor should be slowly ramping up to this desired speed. And on the other hand, we have a closed loop configuration, which adds a bit more complexity. It takes speed readings from the onboard sensors and compares it to our desired speed that we discussed in the open loop configuration. It then passes this through a PI controller, and after some calculations, we have a value which we command the motor primary to move faster by the calculated value in meters per second than the secondary. Here, we see a visualization of the 3-phase sinusoidal system and its equivalent space vector on the left. The goal of space vector pulse wave modulation, or SVPWM for short, is to generate a rotating magnetic field in the primary of the motor, which causes the secondary to so-called chase the primary. This in turn creates thrust. SVPWM uses some basic linear algebra to determine how to switch the motor controller switches so that we can recreate a magnetic field pointing in any direction. We have to do this calculation about 10,000 times a second. This is also referred to as the switching frequency, and it can vary depending on a number of factors. This frequent switching is done to create a smooth rotating magnetic field. Next, the PID controller. A PID controller, or a proportional integral derivative controller, is a control loop using a feedback loop that continuously calculates an error term as the difference between the desired and measured values. The controller then applies a correction based on the proportional, integral, and derivative terms, hence the name PID controller. The controller has three parameters that must be tuned in order to achieve stability of the system: K sub P, K sub I, and K sub D. These are real coefficients corresponding to the error, the integral of the error, and the derivative of the error. The signal from the compensator is then the sum of the three terms. For example, let's say you're driving a car at 50 kilometers per hour and notice that the speed limit is 80 kilometers per hour. You then match the throttle, and as you approach 80 kilometers per hour, you gradually take your foot off the throttle. Once at 80 kilometers per hour, your input is near zero. This is an example of proportional control. The throttle is proportional to the error in speed. And the integral term. The integral term prevents overshoot. Suppose your controller overshoots, surpassing zero and creating a positive error. Your proportional controller will tell the plant to keep going further. The integral term prevents this runaway by keeping a sum of all previous error values. And if the integral of the error surpasses zero, the controller corrects the overshoot. As for the derivative term, well, in our model, we actually exclude the derivative of the error. This is because noise may make it too difficult to calculate it accurately. This exclusion can result in a system which is less responsive to state alterations, called a PI controller. However, this is arguably more common than a PID controller.
So now on to gate driving. This is the main component of the board. As Dev mentioned earlier, we use SVPWM to drive the MOSFETs. The gate driver sorry, I think we cut out. Okay, so the reason why we went with this specific gate driver was that as a team, we already had experience with the 8305 from a developmental board, and the 8323 was essentially a better fit for the application as it can handle enough sync and source current. In addition, at the time of purchase, there was no stock shortage for this chip. So the chip is also highly integrated with features such as slew rate control and adjustable gain for the current sense amplifiers. So now I'm going to talk about the three-phase inverter. So the three-phase inverter is shown on the screen. We use N-channel MOSFETs in a triple half-bridge gate drive configuration. The N-channel MOSFETs have a lower on resistance, consequently causing the power loss to be lower, which is optimal for high voltage applications. These MOSFETs act as switches and are designed so that at any time 3 MOSFETs would be closed, and by using this configuration, we're able to convert DC to variable AC, which is needed to move the LIM. While designing the boards, we made sure that we considered various safety performance considerations. We included DC link capacitors at the battery input terminals to limit the fluctuations to provide a stable DC voltage. In addition, we added lead resistors parallel to the battery to discharge the DC link capacitors when the power supply is turned off. Now I'll talk about some safety considerations while creating the layout for the power board. These included having short, high current paths to minimize inductance. The widths of the traces were also chosen to be large enough to allow for more current, as well as making the clearances between the traces wide enough to prevent arcing. As mentioned earlier about sourcing, I mentioned that the DRV-8323 is well integrated. A safety feature that I mentioned earlier was slew rate control. Besides that, an important safety implementation in the chip is that it includes an internal state machine, which adds a dead time insertion. And this is to ensure that the high side and low side MOSFETs don't cross conduct to prevent shoot throughs. So on the power board, we have two types of sensing. So for current sensing on the board, we use shunt resistors. These are low resistance resistors, and basically the current flows through the resistor to generate a voltage drop that's measured and amplified by the DRV to be sent to the logic board, and then the amount of current can be solved using Ohm's law. And the voltage sensing is done by using a high impedance dividers to attenuate the phase voltages to be sampled by an ADC.
Thank you, CHC, for giving us the opportunity to talk about what we've been working on these past couple of months, and we hope you enjoy the presentation today. Now I think we'll be opening the floor up to any questions.
Thank you very much for this impressive presentation on your system. I'm really looking forward to the questions on that. And as before, if you have any questions, simply type it in the chat or raise your hand and I will call you out.
This isn't really a question, but I saw in the chat someone like the Vulpix PCB. So a funny thing is for every electrical board on our team, we use a Pokemon to name it. So.
Okay, I see there's actually one question. Have you factored in or calculated temperature for your PCB design, I assume?
We kind of did it backwards. So right now we're going through the design through PSIM. So right now I'm debugging PSIM and hopefully we can get the power losses and temperature efficiency through that.
Yeah, so just to recap, PSIM is a software we've been using to simulate a lot of the control theory and the functionality of our boards so that we save some time in the development process. And something that allows us to do is even get simulations for how temperature is going to affect the rest of our system.
Just let me read it once out. I see there's another question. Just wondering, why did you choose PSIM for control system simulations? Does it have any specific benefits over other tools?
Yeah, so PSIM was actually chosen by our previous motor control team lead, and they're actually a proud sponsor of Waterloop. Something that we definitely use PSIM for is, as we mentioned before, simulating the actual functionality of our board and performance, but it's also very useful when we're doing things like tuning PID values. Mm-hmm. It has a functionality called Smart Control, which allows us to sweep through the values and save a lot of time instead of doing it manually ourselves. Additionally, they also have a little interesting feature was called code generation, and this also saves us time when we go on to actually testing the actual board. Instead of having to write up all the code ourselves, PSIM actually speeds up a lot of our development process.
Another thing that we use it for, it's really useful when you're trying to mimic the actual board because, for example, like the specific MOSFETs that we use, we can put the exact values of that in the PSIM and then so that it's not an ideal MOSFET and you can change the levels with different parameters. So you can kind of like mimic the MOSFETs that we purchased in the simulation.
Okay, since there seem to be no further question, I would say we wrap this round, but once again, a very impressive presentation and can't wait to see your system in action in person next spring. Thank you very much.
Thank you.
Thank you.